Yeah. So good afternoon. Appears the others are not joining. All right. So uh, we'll continue from the last lectures where we introduced ourselves to a number of concepts uh, on automata theory, right? We were able to establish that automata theory is a self-propelling machine that is able to transit from one state to another upon the receipt of an input from uh, an alphabet of a language or from a grammar of a language. And it moves from what is called the initial state through different states up until it gets to a state called the final state. Also, we made a formal definition of what a finite state automata is, right? We said it has a set of states, a set of input symbol. It has a transition function. We have a Q naught, that is the initial state, right? And we also have a QF or F, which is an element of the state, being the final state of the automaton, right? And we also try to look at how we could or we read uh, input symbols from an alphabet, right? And we said that an automaton being is maybe a movement from stage to stage, right, has very limited memory. And those memory is just to remember after processing a transition from one state to another, it's able to remember the states that you can be, right? So those are that's a summary of what we did in the previous class. So in today's class, we'll be looking at Introduction to Finite State Machine, which is just a bit of a review of what we did last week, and also stepping it further to a more a well-defined, more maybe a little higher in the hierarchy of automata. So, as a form of introduction, we introduce a finite state automata or finite state machine is a machine that is capable of moving or transiting from one state to another, right? That means it is capable of moving from state to state, and the movement does not just take place. So the transition occurs upon the receipt of an input symbol. So we have in our first class, we define what symbols are, right? We define what alphabet are, and we define what languages are. So this transition occurs upon the receipt of an input symbol, right, from a set of alphabets of a language. Now, please take note of this definition. We said this transition occurs upon the receipt of input symbol, right? Now, we said the input symbol are usually read from left to right, and only one input symbol is read at a time. And upon the reading of one input symbol, there is a transition from a state. Let's assume that it's the first state called the initial state to another state. So when it gets to that other state, another symbol is read from the input symbol, right? So, and we also argue that the input symbol is from a set of alphabets, right? So the input symbol is not just arbitrary. It must be from a set of alphabets. Not only that, those alphabets should have laws governing their formation, and that is a set of language. So it starts as the initial state and transits from state to state until it gets to the final state or the accepting state. So that is the movement of an automaton. Last week, we defined what some of these states are, right? So, but this week, we're going to be seeing another kind of representation. Now, this is just to buttress the point I said last week, that you could define any, you can use any alphabet or any representation to represent definition of your finite, your automaton. The only thing is that you have to define it formally. Now, last week, we're looking at D, right, as the state, or Q naught. But here, we have a different set of variables. Now, I said a set I called the input alphabet. So here, we have defined capital I as, no, a set I called the input alphabet. That means the input symbol, it has been defined as what? From, okay, the input symbol has been defined from a particular alphabet called I. Then a set S, whose elements are called states. So here, states is defined as S, as against Q in the last class we had. Now, a function T as against the P that we saw last week, which is once you are at a state, and upon, okay, let me put the annotation. So here, you say once you are at a state, right, and upon the receipt of an input, once you are at a state and you receive an input, now that means you are in any state. So S can be of any of these, S0, S1, S2, etc. So once you are in any of these states and you receive an input symbol from I, right? And that could be your I1, I2, I3. Starting from the left, you receive an input symbol from an alphabet, then you move to a state. That means you move to another state, which is an element of the global state, right? Called the transition function. Now, a peculiar element, which is S0, which is an element of the global states, called the initial state. So we define a state called this S0. That means it's the initial state. And you remember, we said any initial state is pointed to by an arrow. Now, the functioning of the machine is as follows, right? So let's look at the functioning of the machine starts at the initial state. The machine starts at the initial state. Of course, you know that once you have a state, which is S0, there is an arrow that points at it telling us that that is the initial state. So this is our S naught. So this is S naught. Okay. Now the input is a string of character. A string of character or a string of symbols from the input alphabet, which are read one at a time from left to right. I think that is well explained. So at each stage, the machine is in some states S, which is an element of the global state S. If the machine is in some state S and the next input character is C, which is an element of I, the machine moves to state T, it moves up others, you're at a state S, which is a subset or which is an element of a global state S, big S, and you receive an input symbol C. Then you move to another state S, which is also a subset or an element of S. So what it means that you are at a state S, which is a subset of, and you receive an input symbol, let's say C. You move to another state S, which is also a subset of the big S. So you are at a state S. Let's say this is S1. You receive an input symbol C, right? You make a transition to a new S, let's say S2, which is, oh, hello, can you see me? Hello? Yeah, please, you could type yes if you can hear me. Oh, okay. I thought I was thrown out. All right, thank you. I can see that. And still hear me. All right. So, um, so if the machine is in a state, so that means you move from state to state and await the next input character. The process continues in this way until all the input characters has been processed. That means all the input character of I has been processed. That's when the input symbol, maybe that's when the states, or that's when you stop expecting any input to make you move from states to states, right? So moving on. Now, we said that the states machine can be represented in two forms. The first one is the state table, and the other one is the state graph or the state transition diagram. Now, of course, we have been able to look at one of them. So we're going to look at what and how to go about drawing some of this. So this is what is called the state table, and this is the state diagram, right? So you have a set of states, then you have input symbol, then you have the output for those that needs some set of output. So don't pay, this is just for example purpose. So by the time we move, you'll be able to understand it in now let's look at an example to illustrate what we have just explained so far, right? So we said, given the following, right, we have defined our input alphabet to have the input symbols 1 and 2. input alphabet having input symbol or input character 1 or 2. Then we say that we have our states given as A, B, C, and D. And it has been established that S naught, which is an element of big S, is the initial state, right? So the transition function is given by this table here. Now, note that the arrow is used to represent the initial state on this table. As we have said last week, we say that the arrow will point at a state S naught. So the same thing that is here on the table. So how do we now transfer them into a form of diagram or into a form of a state table? The first thing we draw is the set of, we count the number of states that we have. Now, according to this example, can somebody tell us how many states we have here? How many states do we have? Please just type. Yes, we have 4 states. Okay, thank you. Abdullah, Azana, Yomide, Orishadari, Lufemi. Thank you. So do we all understand how we arrived at 4 states? So you arrive at 4 states by just counting the number of states that has been given here. Oh, sorry. Let me clear all this. So this is how we arrive at the number of states. This, and this. So that's how we arrive at the number of states. So the next thing we draw, so you draw the table. So that's the table being drawn. Now, what are the input symbols? The input symbols are what? 1 and 2. So this is where the inputs will be. Input will be on this line. So here we have 0, 1 as the input. Now, this is where the states will be. States. So how many states do you have? You have 4 states. So you put A, the first state, B, the second state, C, the third state, and D, the fourth state. So you can see. Then you have an arrow pointing towards A, telling you that that is the initial state according to this scheme. So that is how to draw the diagram generally, the state table generally. So if you're able to draw this, then you now look at your state diagram. Okay. The inputs are 1 and 2. Yes. Thank you. Oh, sorry. I think I made a mistake. Clear. So here. So the inputs are 1 and 2. Yeah, thank you. Right. So you now look at the set of states. You have A, B, C, E. So these arrows. So this is how to translate from a state diagram to a state table. So it now said this is how the process of transition occurs. Now let's interpret this table together. This is telling us that this is where we will start reading our input symbol. So according to this transition function, which is defined informally as T, when you are at a state S, which is an element of the global set, and you receive an input function I, or input symbol I. Then you move to another state, what? S, which is also an input symbol. So this is what it means. So let's look at how this can be interpreted on this table. So here, we have been told that this is our initial state. A is our initial state. So let's assume that according to this scheme, what it says is that once you are at A and you receive a 1, you move to B. Should I come again? Once you are in state A and you receive an input of 1, then you move to a state B. So let me explain that using a diagram. So we have this T, S, comma, I, then it moves you to where? Moves you to S, a state. So on a diagram, you have this. You have this being pointed to. So you have this as our A. Do you still understand up to this point what I've just drawn? Yeah, do you understand what I've just done up to this point? Okay, so let's do you have anybody who have a concern or question at this point? Okay, so we understand. Okay, so we assume that you all understand. So I'm trying to interpret this table for you to understand easily. So we say this is the initial state, this is the initial state. So now, according to this transition function, which is when you are at S and you receive an input character or input symbol I, then you make a transition to where? To S. So, okay, I think somebody is here. Okay, I'll send that. So when you're at A, here, you receive a 1 according to this scheme. Here, you receive this 1. Where did this say you should go? Here's the arrow. You receive a 1. It says you should go to where? B. So this is B. Now there's another scheme. Say you are still at A. You receive an input of 2. It says you should go to C. So that means you create another point called C. So it says you are at A, initial state. You receive an input of 2. You move to state C. So you are at A, here, this is A. You receive an input of 2. Then you move to C. Do we understand that position? If you have any question, just raise up your hand. I will let you speak. So, do we understand up to this point before I move forward? Okay. David. Okay. Okay, you can unmute yourself.
Okay, sir. So on the last row where we have the entry for like when the input is 2. Normally, I was expecting we'll have the A then B, like 2 is end up in B, but it's ending up in C. So I don't know why is that. That's my question.
This is just an example. We're using this as an example just to explain the concept. We have not formed any thought yet. We're just using it to explain the transition function. Now, I said your thoughts will be guided on how the transition function works. All you need to do is to test if the input string given is accepted or can move through the states easily. Okay, so let's continue this place. So this is 2. Now the next one, you're at B. So you are done with your A now. So A is done. So the next one, the next state is your B. So here he said you're on B. This is B, and you receive an input of 1. You move to C. So you're on B. You receive an input of 1. You move to C. That is according to this transition function. Another one, you are in B. You receive the second input. So you are in B. You receive a 2. You move to D. So you are on B. You receive input 2. So you create another state, D. So you're on B, receive an input 2. You move to D. Furthermore, so you are done with B. The next one is C. You're on C, you receive an input of 1. You move to D. So here, you receive an input of 1. You move to D. Then you're on C, you receive an input of 2. Oh, sorry. Okay, it's correct. Then you're on C. You receive an input of 2, move to A. So here you're on D, move to A. So let me draw this. So now please watch. You have this. So you have like a loop to tell us that it's not continuous. So you're on D. You receive an input of 2, you move to A. So here you have 2. So you are done with C. The next one is D. So you're on state D now. You receive an input of 1. Oh, sorry. I think this, we made a mistake here. This is C. Let's go back to C. This is C. You receive an input of 1. You move to D. You receive an input of 1. You go to D. So you're on C. You receive an input of 2. You move to A. So C to, you're on C. Okay. This is 2. You move to A. So here, you're on D. You receive an input of 1. So here, this is 1. You move to A. Then you're on D. You receive an input of 2. You move to C. So here, you receive an input of 2. You move to C. So aren't we supposed to move from? Okay, I think that's what I've just corrected now. Yeah, so do you get the explanation now of this diagram and this table now, according to this transition function? Okay, thank you. But does anybody have any question or concern? Any question? All right, so let's move on quickly. So that is how we'll be interpreting all the movement as we go on. Now, I have to waste some time here so that at least a majority of us can understand the concept being explained. Okay. So now let's look at this scheme again. Let's suppose the inputs of the machine is this. So assume that this is the input symbol, right? This is the input symbol. That's all of this. Let's assume that all of this are the input symbol. And we are told to pass this set of input symbols through that same state table we have in the previous page, which has been moved here. Now, let's see ways that we can use in moving that. So please pay close attention to this now. This is the transition function, right? Which is when you're at a state to receive an input symbol, right? Input symbol I, then you move to another state, S. And these two states are the elements of DS. So look at this table clearly, and let's try to pass in this input alphabet. The first one is what? 1. The second one is what? 2. No, 1. Then the next one is what? 2. Then 1, 2, 2, 1, 1, 2, 2. So that's the scheme. And we start from where? From the left to the right. So here. Now, don't just want to see how this was arrived at so that you understand this easily. Now, look at this table first. This is where we'll be talking from. Then we'll be writing it here. The first input is what? 1. And the initial state is what? A. So you write down your A, right? The input that you first of all read is what? 1. So here, you are at A, you read in a 1. Where you're supposed to go to? You go to B. So here, you write B. So you can see you're at A, you take in 1, you go to B. Do you understand? Do you understand up to this point before I move forward? Okay, thank you. So the feedback I'm having is that a number of you get what I'm explaining. All right, so going forward. Now, you are now done with the first input. So, but that input that you have taken has taken you to where? A state B. So you are done with state A now. You are now on state B. What's the next input? The next input is 1. So you are in state B and you read what? A1, because that's the next input here. Here, 1. So you come to this state B. You read an input of 1. What state is it carrying you to? State C. So you're writing your C here. So you are in state B. You read a 1. On the table or the transition function, it says it takes you to where? C. Right? So this is where we have our C. Okay. Then the next one is you are now on state C. This is state C. The next input symbol is what? 2. So it said you are in state C. You read a 2. Where will 2 take you to? When you are at C, it will take you to A. A. So this is where you have on reading 2, you go to state A. Now you are on state A. The next input is what? 1. So you are on state A, you read a 1. It takes you to where? B. Now you're on state B. The next input is what? 2. So when you read a 2 at state B, it takes you where? A D. Do you still get it? Are you still okay? Yes. Okay, do you still understand up to this point? Okay, so can somebody continue from state D? Can somebody raise up his or hand to explain to us how we move from state D to state C? Where is this Joseph? Okay. There's one who form. Okay, I'm coming. Vice, I'm coming. Okay, so Ufodrum, Michael says he doesn't understand that it's lost. And also Joseph Ola Nyoju said it's lost. So let's look at those whose hands are raised up. So Pfizer raised up his hand first. So you can unmute to explain to us.
So from D, it's taking an input of 2 to C. Then from C, it's taking an input of 1 to D.
No, you should explain to us how that is done.
From D, it's taking from the state table. D
Okay,
is
from the state
going,
table,
yes, for D.
upon the
has-
receipt of 2,
Yes.
it goes to D.
No,
Is
from
that-
D goes to, yes, from B goes to D, yes.
Okay, so I think that's correct. So let me clean so that I can allow. Okay, thank you,
Yes,
Faisal.
sir.
Okay, I think there's another person who wants to speak, and David is on. So you can speak.
Exactly. So
Yes.
so it's moving from D to C.
D.
It moves from D to C because on the table that we have,
Is the table.
the input is 2. When the input is 2, when the input is 2, it ends up at C according to the table. So this table is the guideline. The table is the guideline we are using to get the inputs, then get the result. So whatever the beginning one is the A. So when it receives, we now use the inputs, this string of input 1 1 2 1. So once it receives 1, it moves to B according to the table. Then the next one, it is on B. So the next input is going to be entering B. So when it receives B, when it receives 1, when that B receives 1, according to the table, when B receives 1, it's supposed to end up at C. So you see C there. Then same thing with next one is on C currently. So the next input is 2. And according to the table, when we receive C, when C receives 2, sorry, it ends up at A. So that's just the pattern. That's the pattern I'm
Okay.
seeing.
Thank you. I think the next person is Show Bandit Milane. Yes.
Yes, sir. So the C is taking an input of 1. So it's going to be to the state D. So the D is going to be taking the position of input of 1 in the C state. So if the D is taking an input of 1 to a state of A, then the position A is going to be under the input of 2.
Now, I think you should be, thank you. I think you should know that this is, when you have alphabet A, the input is on the arrow, not on the state. Now, because of the space, that's why it looks as if it's on the arrow. Then it moves to a transition B according to this scheme. I hope you get that. So I think somebody said he doesn't understand. So for Don Michael, please can you raise up your hand so that you tell us what you don't understand? Then we can explain from there. And also Joseph or Lion Chu, so that I will know where you got lost. Okay, Lion Chu Joseph. Okay, so you can speak.
Okay, no, I got it already.
Okay, I think I saw in the chat you said you didn't understand.
Yes, with the explanation now, I think I'm good. I got it already.
Okay. Yeah, I think somebody is canceling something. Okay. Shubandit Milayin. So you can speak.
I think I said I was trying to explain more on the states with the input, which I did.
Oh, sorry, I think it's Opodum that I wanted to call, but the individual is not raising. Okay, from B. Okay, Opodum right is raised now. Okay, so let me look for you. For June. Okay, so you can speak.
I'm talking about from the first input of B. I don't understand down to the second C. Down to the first C. Down
This,
to the
right?
first input. Yes, sir. That's it.
Okay. All right. So say it doesn't understand from this point. Now, you understand that this A is the initial state. So we put our A here. So the first input string is, now look at this here. This is the input string we want to pass through this machine. So it tells us that A is the initial state. So we start at A, which is the initial state. So you must be at a state before you start reading the set of input. So the first thing you will read here is what? 1. So we have read the 1 here. So you now come to this table. You're on state A. You pick up an input of 1. Where is 1 taking you to as state A? It's taking you to B. So you put your B here. Do you get up to that point of Fordham? Or Fordham, we are waiting for you. Okay, so now, so you are done with state A now because you have read an input symbol that's taking you away from state A to state B. So now you are now on B. Now the next input symbol is what? On this input this thing is what? 1. 1 again. So you put a 1 here. So how do you decide where you go from B? So you go to state B now. This is state B on the state B is state B. So once you read a 1 as state B, where does it take you? This is C. This is what is under 1 as state B. So here you move to C. Do you get it? You get it now? Fordham. Okay. So now you are done with state B, you are now in state C. The next input string is what? Input symbol is what? 2, according to this input set. So you have, on this input, you have what? 2 that is read. So you go to state C. You look at 2. Where is C taking you to? Under 2 is taking you to A. So this is A. Yes, I hope you get it now in that direction. Of Fordham. Oh, okay, thank you. So now I understand. So, all right, so we can move on from here. So I'm sure you should be able to also know how we got all this set of transition, right? So on the last one, this is the last input that we are reading, and we are state C already. So when we read a 1 as state C, a 1 here as state C, it takes us to D, and that's where we arrive at this point. So you should be able to read the table and the input sets that you have. So moving forward. So we have been able to see a machine, right, that is able to read, maybe take our input, read the input, and move to the next state. However, that is a limited kind of computer, or that is a limited form of machine that we want to play with or want to work with. As a matter of fact, it will waste our time even further. So there's a need for us to come up with an improved machine that's able to do more than just reading input symbols and remembering where the state is or it is upon the receipt of an input symbol. So if you get an input symbol, there's a transition, which means a movement from one state, the previous state, to the next state. That is all the other machines can do. However, there's a need for a machine that is able to take in input symbol from input alphabet defined over a language and is able to take us from one state to another and give us an output. So in that light, let us consider a machine called the Mealy machine. So to be of any use in computation, a finite state machine must have some form of output. An obvious way to have the machine print it out. We need an output alphabet. You can see we have introduced another formalism or another variable called output alphabet. Now, so before we had our input alphabet, we have, our input symbol or input alphabet, right? We have our transition function. We have our initial states. We have our final states, right? And we have set of states. So now we are now introducing an output alphabet now. So making that a Mealy machine is a 6-tuple with what? Inputs, states, input alphabet or input symbols. It has a transition function. It has set of states. It has initial states. And it has an accepting state. It also has an initial state. Now, and so we need an output alphabet, which is a big O, that may or may not be the same as the input alphabet. Now, please take note of this writing. It said the output alphabet may not be in the same league with that of the input alphabet. So that means if you have your input alphabet to be ones and zeros, maybe input alphabet is 1, okay, let's say 1 and 2 as we just did. The output alphabet may be Z, X, maybe CD. What was before Z? Y, okay. It may be, your output may be Y and Z. So they may not be in the same, they may not be in the same inputs alphabet. They may not be the same. So take note of that so that at least we'll be getting to, okay, maybe when you get to a more complex state, you will know that, okay, you don't have to have 1, 2, then maybe the output is going to be 1, 1 and 2 again. So the input may be 0 and 1, and the output may be A, and it will be in this range of alphabets. Okay, so to describe the output of such a machine, we need to have an additional function that assigns to each combination of states and input character and output character. In other words, we have a function P, which is defined by at a state S, which is an element of big S. Upon the receipt of an input function, you move to another state while sending out an output. You know, the former one is just you're at a state, right? Upon the receipt of an input symbol, you move to a state. That was all. But here we are extending it that once you are at a state S, which is a subset or an element of a global S, and you receive an input symbol I, you move to a state, but now it's been extended to that you output a big O, which is the output. That means you are printing an output for us to see very clearly. So in other words, we have a function, this. When the machine is in state S and reads the character C, the output is what? P of S comma C. Okay, so a machine of this type is known as the Mealy machine. So a machine that is able to function in this way is known as the Mealy machine. All right. So going forward, so this is an example of a Mealy machine, right? So you see in the formal notation we have before now, we just have like you are in a state, you receive one input, you move to another state. But what you see here is that you are in a state, you receive an input, let's say an input of 1, then you output something, maybe 1 or 0, and you move to another state. So that's the working of a Mealy machine. You are at a state S0. Upon the receipt of an input, you move to state S1 and you output 0. So what it's saying is that the printing is dependent on the transition. So if you are going to print, you must be leaving the state before you print. So here, let's assume that I'm here and I'll say, okay, read 1, print 0. So what it says that you must first of all read the 1 before you now print the 0. Do you get what I've just explained? Or do I come back? Should I explain again? Do we understand or do I explain again? Okay, so let me explain again. Here's what he's saying. We have just explained that we needed a system that is won't just be moving from state to state and just remembering the state alone. We need a machine that is more powerful in such a way that it can move from state to state, right? But if you move from state to state, remember the state and also print out an output for us to see. So let's assume that this is state A and this is state B. And you have a kind of input like 111, 1101. So let's assume that this is the initial state, and you pick up an input of 1. You know, that is a normal finite state machine. But for a Mealy machine, it will not just transit from one point, from one state to the other, but it will give us an output 0. So this is the input here on the left, then the output is what? On the right. So this is what we are seeing on this diagram here, where you have, you're at S1, this is S1, you receive an input of 0. You move to where? S2, and you output 0. So this is the interpretation. You receive 1, you output 1. You receive 0, you output 0. You receive 0, you output 1. You receive 1, you output 0. Do you understand now? Is state S2 the start state, sir, because the arrow points into itself. Now, that is not the case here, S2. Now, what we said about initial state is that the arrow comes from nowhere. So you can see this one here. The arrow is coming from S2 and pointing to S2. So it doesn't mean it's the initial state. There is no arrow indicating the initial state in this diagram. This is for example purposes. But if you want to look at it holistically, once you look at our numbering, 1, 2, 3, if there's no initial state indicated, then you know that the first one, which in the regular numbering, is your initial state. Do you understand that? Somebody wrote a question, that's what I'm responding to. The person said, is the state S2 the initial state, because one arrow is pointing at it, and I think it's referring to this arrow pointing at it. No, it is not the initial state, because the arrow is emanating from S2 itself. But in our definition of initial state, it must point from nowhere. So it will just appear from somewhere and point to this to a particular state. All right, so moving forward. S1 should be the start state. Yes, according to numbering. But if if it is not stated, then you don't assume. Okay, so look at this state table. We have that it has been indicated here that our initial state is what? A, right? Then, okay, now can you also my table, my slide? I want to quickly explain this. So this is telling us that this is the initial state. So we assume that you understand this arrow pointing at A is the initial state. So how did we come about this table? So thank you. So the table is that you have a set of states, which is denoted in our parlance by S, and the set of output table, output symbol denoted by big O. Look at this and follow very quickly. Now, here, you are at A. This is A. You receive a 0, an input of 0. It tells you to go to where? A, and output 0. Let me explain that again. Okay. Now listen again. This is your initial state. You have the inputs symbols and you have the output symbol. In this case, they are the same. So how do you read this table? This is how you read it. You are at A, right? You read a 0. It tells you to make a transition to A. And your output is what at that instance? 0. So this is it. You are at A. You know, you have this arrow pointing. So you're at A. You receive an input of what? 0. You move a transition to where? Sorry. Let me clean it and start it over. Okay. So this is our arrow showing that we're at A. So you said here, you're at A. You receive an input of 0. You're at A. You receive an input of 0. You move to A. So you're at A. You receive an input of 0. You move. It's still pointing at A. So the input is what? 0. This is the input. Input. Then now the output under A, under 0 is what? 0. So here the output for you is 0. Do you get what I've just explained? A response? But if you have a question, you can raise up your hand. Okay, so thank you. Okay, so I can see a number of people get the point. So the only difference in what we have done so far is that there is an output. So let's continue. The next one is that you are still on A. You receive an input of 1. You go to B. So let's assume B is here. B. So you are at A. You receive an input of 1. So this is an input of 1 from A. An input of 1 from A. So it says you go to where? B. And you have gone to B. And what's your output under 1? The output is 0. So this is the output. You're at A. You receive an input of 1. You print 0 and you go to B. Do you understand that? Hmm? Is that clear enough? All right, thank you. So moving forward. So I'm sure you can now interpret all these tables. So here it said, once you are at B, you receive a 0. You go to C, you output 0. You are at B, you receive a 1. You go to D, you output 0. Here, once you are at C, you receive a 0 input. You move to A, and you output 1. Still at C, you're at C, you receive a 1. You move to B, you output 1. Now, in that case, so if the input is this, then the output will be this as shown below. So let's see how that output will be, so that we can now move forward very quickly. So look at this diagram here. Now, this is, okay, let me clean it. So this is the inputs we have. And this is the scheme, the table that we have, the transition function. I want to test this input string. The first input string is what? 1. So the initial state is A. So we'll write out the initial state A, which is here, right? So the initial state is A. So the first input string is what? 1. So this is so let me just draw it here so that it will be easy. This is our A. So you are at A, and the first input we have is what? 1. So we'll come to the table. We're at A. This is A. We receive an input of 1. Where did he tell us to go to? So we should go to B. So we write B here. Now, our definition of a Mealy machine is that the output is given out based on the transition function. So, and this is the transition function, this arrow. So we now say, okay, you're at A, you receive a 1, you move to B. Now, what is the output of 1 here? You're at A, you receive a 1 here. So the output under 1 is what? 0. So the output here is what? 0. You get that, or do I explain again? Response, do you get that, or do I explain again? Okay, in this diagram showing the successive transitions are the transition, sorry, let me see what this question is written. In this diagram, okay, in this diagram showing the successive transition are the transition with input of 0 and output of 0 ignored. I don't get that question. Okay, somebody here understood. So let me explain for that individual who has not got it. Now, listen again. This is what we are saying. We have 2 sets. This is the, okay, this is the demarcation. This is the input side, right? This side, this is the input side. This is the output side. But what you have to look at is that whatever the input is, we judge what the output is. If you receive a 1, you come here to check. That's input 1. And you also check the output under 1. If you receive a 0, you come here to check where it will go and where the output will be, right? So now we say we are at A, and want to test this. You want to test this input symbol or this input alphabet, right? So you at A, you receive an input of 1. You receive an input of 1. So this is A. You at A, you receive an input of 1. It takes you to where? B. You at A, you receive an input of 1. It takes you to where? B. So you at A, you receive an input of 1. It takes you to B. Yeah. So what is the output? How do you get the output? The input you receive is a 1. So you still go to this side where there's 1 and you check what the output is under A. And the output is what? 0 under 1. So this is where the output is. Look at the next one. You have a 1. Now it means that you are B. You receive an input of 1. Now, so this is B. You receive an output of 1. Where does it take you to? D. Right? So you are B. So you have moved to D here. Now, what is the output? You are B. The output under 1 is what? 0. So this is the output you have here. Now, moving forward, you are D. This is D now. Here, you move, go and check D. You receive an input of 1. You are D. You receive an input of 1. This is input of 1. So where do you go? You go to D. This is D. And what is the output of D under 1? It is 1. So this is the output here. The next one is that you are still at D. You receive an input of 0 from the input string. Now you are D. You receive an input of 0. Where does it take you to? C. It takes you to C. And what is the output of D under 0? The output of D under 0 is what? 1. So this is where you see this 1. Now, you are now at C. At C, you receive, this is C. You receive an input of 0. You go to A. So you go to A. And what is the output of 0 on under C? So this is 0. The output is 1. So this is the output. Now I'm sure that you could understand. Okay, hence the input and transition states can help us determine when the what the output will be, all based on the table. Yes, this is a transition function, and it's a transition function, which is the table that is going to guide our movements here. So we look at the input. We have been given the input. We have been given the table, and we are told to produce this. So assuming that we are doing it one after the other, you won't have seen the whole this thing. We'll just be doing one after the other. So you have A, right? You read a 1. It moves you to B, right? Then your output is 0. So that's the first thing you see at the first stage. Then you continue again to D and all that. So it's because this is a slide and it has to be pre-shown. That's why you're able to see the whole output. So the table will guide you in your movements. I hope that is clear now. Okay, thank you. So moving forward. How come it jumps at the end like that? Children jumps at the end. Okay, this is where we are. So the next one is a mob machine. An alternative arrangement for output is to have the machine print a certain output character as it enters a state, right? So these machines are called mob machine. So now what he's saying is that instead of printing the value of, this is the this is the input, right? This is the output. So instead of having this form, another form is that instead of saying, okay, when there's a transition that you print, another method is just printing straight with the state you print in the state. So you are in a state, this is the output. You move to another state, B, right? You print the output straight on that state instead of having a transition function. So let's read that so that we can understand that concept first. So an alternative, so we are looking at more machines now. An alternative arrangement for output is to have the machine print a certain output character as it enters a state. These machines are called more machine. The output is attached to the states rather than the transition. So you can see the output is attached to the states rather than the transition. Formally, the output of a more machine is described by a function P, which states that if you are in a particular state, print the output. Whereas before, the big O is the output alphabet. So this big O is the output alphabet. So the following more machine is also a two-step delay machine, behaving exactly to the middle machine in example above. So here we have that our input symbol and our output symbol, they have the same, no, our input alphabet and the output alphabet, they have the same symbol. And we have the states A, B, C, D with our S0 being, our A being the initial state. So S0 has been defined as our A. Okay. So look at the state table below and try to pass the following input. So you can see this is the state table guiding our movement. This is the state table. This state table is guiding our movement or our transition, kind of, right? And this is a set of input one test. This is the table. So what is the saying is that once you are state A, print 0. As state B, print 0. As state C, print 0. As state D, 0. E, 1, 1, 1, 1, like that. Right? So let's now see how we can test. We can test this input that we have. So we are at a state A. We are state A. We receive an input of what? 1. So in milli machine, we are supposed to send in an output here, but here we are not going to have any output. All we say is that the output, sorry, let me clean. Okay. So at state A, you receive a 1. Your transition is what? To B. And what is the output function on B? The output, big O on B is what? 0. So the output is what? 0. The next one, you're on B. You receive the next one. You're on B. You receive the next one. What state does it take you to? You're on B. You receive a 1. Move to D. So you move to D. Now, what is the alphabet? What is the output alphabet on D? 0. Now, you are now on D. You receive a 1. You're on D. You receive a 1. You go to where? H. What is it? Now, you now check it. What's the output alphabet on H? It's 1. So the output alphabet here is what? 1. Then you're on H, you receive is 0. You're on H, you receive a 0. So you're on H, you receive a 0. Where does it take you to? It takes you to G. What is the output alphabet on G? it is what? 1. And it continues like that. So you'll be given a number of these kind of questions to test the inputs and to show us that you understand the transition of the inputs that we're going to be giving, right? So that is how you must look at the inputs you are giving. You look at the transition function as defined by the table, then you come up with your solution space. You understand this? So we have dealt with Mealy machine and we have dealt with what? Moore machine. So Mealy machine and Moore machine are example of transducers and translators. All right, so moving on. So the next thing we are going to be looking at is what? Finite state acceptor. So we have been able to look at a machine that is able to accept inputs, 1. Then we looked at a machine that is able to accept inputs and make a transition from one point to another while remembering the state you find yourself. Then we looked at another set of machine that is able to read set of inputs, make a transition, remember where you are, and print out an output. So the next thing we want to look at is a kind of machine that can do all of this, but it can determine if a group of string is accepted or rejected. So that's what we want to look at. So as a form of introduction, the focus on finite state machine would be as acceptors for language. So you understand what language from our first class, you understand what a language is, right? You understand what alphabets are, and you understand what symbol are. So given a language on a given alphabet, so a language is defined by a set of alphabets. An alphabet is defined by a set of symbols. So it is important to find a machine that decides whether or not a given string belongs to that language. You know, when we're doing languages, we said that languages are made from certain kind of rules guiding them. So it is not just arbitrary. For instance, we gave an example of using very, very, very good. That at an instance, the use of very, very becomes useless because you don't even know the degree of the excellence in what the person has done. And also we looked at some kind of, semantics and syntactic analysis of language. How? We said that a language can have meaning if it is well arranged and being guided by a set of rules. So this rule is what gives meaning to a language. For instance, we defined S to be equals to S. Then we now say S starts on the S. Then S starts on, I think we were doing a kind of a placemaker. We now define that S is cat and S is also mat. So what the rule of that language simply means is that we could have about 4 different kind of expression in that direction. That means the cat sat on the mat. That's the first one. The next one is that the mat sat on the cat. The other one is what? The mat sat on the mat and the cat sat on the cat. So those are the only languages that could be allowed in that production rule. So languages have production rule, and it is this production rule that helps us determine that, okay, in this set of languages that we have, can a machine be developed that accepts that language? So in this set, we are not just testing if the strings are able to go from state to state. Of course, we are going to test that, but our conclusion lies in the fact that Once we have read all the input string, that means the language, we will now determine, is this input string that we have read over an alphabet defined by a language, is it accepted? Well, now the decision we are taking is going to be in the form of yes or no. So invariably, we say that given a language on a given alphabet, right, it is important to find a machine that decides whether or not a given string belongs to that language. Here, the output is simply a simple yes or no. We are not interested in partial results. We wait for the machine to read the entire input string, and then we are interested in the answer. I'm sure you have started some form of a compiler construction, right? So in a finite state acceptor, FSA, the output is determined by selecting a subset of states as the accepting state or final state. So you know the concept of accepting state already, or final state. That means where the input string should terminate if it's going to be accepted. So if the input string doesn't stay at this state where it is supposed to be accepted, we will say that it is rejected. So if the machine ends in an accepting state, after having read the entire input string, we say that the string has been accepted by the machine. Otherwise, it is rejected. The slight modification to the way we present it as a finite state acceptor on the table is to replace the ones in the finite state column by an asterisk, and the blank and the zero by blanks, so that the accepting states are those with an asterisk against them. So now please pay very close attention to this point. It said that in the truth table, we indicate the accepting state by what? 1. And once we remove the 1, we can put an asterisk to indicate. Now, this is important for the next where we are going, which is called, we are trying to look at equivalence of machine, that if a machine can do a particular work, can we find another similar machine that can do similar work at that rate, right? So it is important that you know that for everyone that is 1, we represent it with what? An asterisk. Any state that is 0, we leave it blank. So anyone that is 1 is what? An accepting state. And anyone that is a 0 is not an accepting state. So it's just an ordinary state. Right? So moving forward. So writing the Moore machine in the example above as a finite state acceptor, we have the diagram in the next. So we have this diagram. Now I'm sure you are confused now because you didn't see the output state. Now remember in the previous line we just read, we said what? The accepting states are represented with what? Asterisk. So instead of me putting 1, 1, 1, 1, then here is 0, 0, 0, 0. So this can be a notation that, okay, this is the output for a Moore machine, right? So you have 0, 0, 1, 1. So if I clean it, you will see that it's just being represented with what? Only asterisk. Do you understand up to this point? Or are you still in class? Are you still with me, or you have run away? Okay, all right. Thank you, Faisal, Ode, Julius, Shubande, Adekola. All right, thank you. And Joseph, Ugorike, Motorayo, Lawrence, Uwechukwa, Emmanuel. All right, so let's continue. So it's good that at least you get it up to this point. So moving forward, we say that the main focus will be on finite state acceptors, right? To every FSA, there is a language, the set of all input string. Now look at it, the language that a finite state acceptor can accept is the set of all input string or strings that are accepted by that machine. You remember when we're defining language and alphabet, where we have something like L star, that's the clean closure, and L plus. That means here, one is able to define any possible combination of the input symbol, including the empty set and that excludes the empty set. So still remember that. Now, we say that an FSA accepts a language L if it accepts every string in L and rejects all other. You'll see, understand that later. I'll explain further. An important question is, can every language be accepted by an FSA? The answer is no. Only for certain languages does there exist a corresponding FSA. For instance, let's assume, okay, let me look for one of your names here. Let's assume that, okay, let's assume, okay, Faisal. Let's assume Faisal is a machine, like a finite state acceptor. Now, what language do you speak? Faisal, am I correct with your pronunciation? What tribe are you, or what language can you speak? Well, she has gone to watch football. Faisal, what language do you speak? Okay. Okay, you can speak.
Fred, Yoruba.
Oh, yeah, Yoruba. Okay, thank you.
Yes, sir.
That means Faisal is a Yoruba. Okay, what other language do you understand?
French and a little bit of Arabic.
Okay, French and Arabic. Okay, thank you. So we have been able to establish that she understands Yoruba, French, and Arabic. So we can now define that Faisal can only understand a language defined over what? French, Yoruba, and Arabic. Right? So these are the set of languages that she can understand. But another individual may just be able to understand only a particular language, maybe a language words, let's say Igbo. So that means if this guy who can speak Igbo or who understand Igbo, and you are speaking Hausa by side or Arabic by side, there is a possibility, or in fact, he's not even going to hear what you are saying. So what we say is that that individual who can speak Igbo doesn't understand the language you are speaking. So apparently, he cannot accept or he cannot decipher or understand what you are speaking in Arabic. So the set of languages that can be understood by Faisal is what? French, Yoruba, and Arabic. So if you speak Igbo, where she's staying or where she is, she cannot understand. So she's not able to accept that language. So if you speak Hausa too, she cannot accept that language. So that is what the whole explanation of acceptance or no acceptance is about. All right, so going forward. Sorry. So how do we now draw the state diagram? Of course, we said earlier that state diagram, finite states automaton are represented using what? State diagram and what? State graph or state table. So it is often convenient to depict a finite state machine. Sorry. It is often convenient to depict a finite state machine pictorially. Now, this is done by drawing a small circle for each state. So we have done this before, but we're just putting it into perspective now, right? This is done by drawing a small circle for each state, right? Which we have done before. So for each of the states, you draw a small circle with the name of the state inside. So the state is state A. So that's the name inside state B. I'm drawing arrows connecting the state to depict transition. So once you draw arrow connecting the states, it is called transition. So the input character that gives rise to the transition is written beside the corresponding arrow. So if the input is 1, it is written by the side of the arrow. So this is telling us that you at A, you read a 1, it gives you a transition to B. So we indicate the initial state by drawing a short arrow pointing to it. So this is the just to depict that, right? So output is depicted in the following ways. Now, for a Mealy machine, the output is written beside. Let me clean this guy up. So the output is written beside the input character for each transition as follows. So you have A, you have state A, you receive, you have state A, you receive an input. So this is the input of 1. This other one is the output. You output 0, and you go to G. So this is how to represent the output. Here, output, input. So this indicates that if the machine is at state A and receive input 1, then the output is 0 and moves to G. So that's the interpretation of the output of a Mealy machine. What about for a Moore machine? For a Moore machine, the output is depicted this way. You are state A, you receive an input of 1, you move to G, and you output 0. You are state A, receive a 1, you output G, you go to state G, output 0. This indicates that if the machine is in state A and receive input 1, it moves to state G and output is 0. So for a finite state automaton, the accepting states are indicated, states are distinguished by drawing a double ring around them as follows. So this is the only difference. For an FSA, you have this. So you can now put this is too small. So you have this. So you have this big. You have another one inside. So anywhere you see a double circle, that means you are at the final state. So what this one is saying is that if the machine is in a state A and receives input 1, it moves to state G. And that stage is the acceptance state. So if that was the last input character on the input string, the string will be accepted. So what you are looking at is that iPhone raised hand. Who is this iPhone? I say you should always come and put your name. Don't tell me iPhone. Yes, what's your concern? iPhone, you can speak. Oh. Unmute yourself and speak. Unmute yourself and speak. All right. Moving on. I don't think he has anything to say. So the following tables and diagrams are the same Mealy machine. So I'm sure you have seen this before. You have that this is the initial state. You can see the initial state. There's a pointer here. This is the initial state. So this table is representing this diagram. So let's look at it together. You are in state A. You receive, okay, let's look at the table, the diagram. So this is A. You receive a 0. It says you move to B. So you receive a 0, you move to B. And what is your output? Your output under 0 is what? 1. So your output under 0 is 1. So you are still at A. You receive a 1. You say you move to C. You receive a 1. You move to C. And what is the output here? 0. Output under 1 is 0. So that's how to convert that. I did, baby. How you say? Who is a Shubande Timileyin? Shubande Timileyin. Yeah, please raise up your hand. Shubande Timileyin, please raise up your hand. Let's see. Shubande Timileyin, please raise up your hand. Okay, so we saw your message. What was that for? Yes, you can speak now. Speak to the class.
It was a mistake, sir. I got the message. So I thought I was replying from the response message. Like the pop-up. I'm sorry, sir.
So you guys are chatting yourself up under my class.
No. As in, from another app, I got the pop-up on the class. I'm on the class.
I understand. So I just thought you guys were having Valentine on my class.
No, sir, not at all.
Thank you. See all these amigos, they have started responding to the messages. Don't mind them. All right, so going forward, now I feel that this diagram is clear enough. So that means I can give you either this diagram or this table. So you can convert from this table to this diagram, or from this diagram to this table. And I can give you a set of string to pass through this diagram. You should be able to do that. Am I correct? Am I correct? Response, please. Do you understand what I've explained so far? That's the question. Okay, all right, thank you. So I think I have about 10 people or 7 people who have responded that they understand. Oh, for Fordham, that's good. It's good to know that you understand this concept. So moving forward. So this represents a mob machine, right? So this is telling us that this is the initial state, right? I'm sure you can see the initial state as A. Let me do my notation. This is the initial state A. So here it says that you're at A, you're at state A, you receive a 0, you move to B. You are state A, you receive a 0, you move to state B, and output 1. And this is the output 1. So you are state A, you receive a 1. You are state A, you receive a 1. You move to C and output 1. You move to C and output, you move to C and output 1. Now, the next one, you are B, you receive a 0. You are B, you receive a 0. You remain at B. So on B, you output 1. On B, you output 1. So you are at state B. You are state B. You receive a 1. You move to D. You move to D, right? So you have moved to D. And what's the output? You output 0. And it continues like that. So do you understand how to change this table to this diagram and this diagram to this table, vice versa? Do you understand that? Okay, so Lawrence, thank you. Faisal, okay, peace, breaks. Opodon, Ami, and Mashaw. All right. Okay, somebody wrote something. We appreciate something. We'll appreciate a quick recap. Okay. So somebody is asking me to do that again. All right. Now, this is a more machine. And the concept of a more machine is that output is attached to the state. Output is attached to the state. So this is the output. This is the output. This is the output. This is the output. So we are trying to look at these two, how to navigate between these two. Now, let's assume that you are given this table, this diagram here, and you're asked to draw this table. So the first thing is that you identify the number of states you have. So you have 1, 2, 3, 4. You have 4 states. So you draw your lines. So you have your input to be 0 and 1, and your output to be P. Then here to be your state. So you put in your states, state A, right? Don't mind where I'm drawing it. State B, state C, and state D, right? So it now says you are at state A here. You are state A, you receive a 0. You receive a 0. It says you move to B. So here, you move to B. And what is the output on B? This is state. You are state A, you receive a 1. You have moved to B. So this is state B now. What is the output? The output is what? 1. So you put your 1 here. Now, you are still on A, you receive a 1. You move to state C. So you move to state C. So what is the output of state C? It is what? 1. So you are done with state A. Then state B. You are state B, you receive a 0. You are state B, you receive a 0. Here, it says you move to where? You remain at state B, and you output 1. So on state B, the output is already 1. Then on state B, you receive a 1, you move to D. You move to D, and you output 0. So state D is here, and the output is what? 0. So you have filled B. Then C. This is C. You're on state C, you receive a 0, you move to A. You are state C, you receive a 0, you move to A. So on state A, the output is what? 1. So that's filled. Then you are still on state C, you receive a 1. Where do you go? You go to state C, and you output 1. State C, we already have an output of 1, which represents what is here. Then we have completed that. So at state D, you receive a 0, you move to C, right? At state C, you output a 1. So there's 1 here already. Now at state D, you receive a 1, you move to state D, the output of state D is 0. Why are you putting your name? Is it time yet? Oh, we haven't finished the class. So we can say that in Moore machine, every state has a fixed output. Yes, it has a fixed output. Right? So I think I've been thrown out of the class. Can you hear me, please? Okay, all right. So please, can you quickly write down your matric numbers and your name? So we'll continue from here the next class. I think the next class, would they have closed the school then? I don't think so. Today is what, 12th or 11th or 13th, plus 7, 20. So we'll see have a class next week. So class rep. So please remind me of the page where we stopped in the next class so that we can continue from here. Okay, so I think I've seen that. Okay, that bridge is raising up a hand. Okay, you can speak, great.
Yes, sir. You said I should remind you of the page, like this particular page, because I don't remember.
Yes, this page, so that when we come next week, we'll quickly run through it.
Okay, sir. No problem, sir.
All right. So let me look for that iPhone that was disturbing the class. So the iPhone is Giwa Abdul Amin. Yeah, 180805023. Yeah, you are raising up your hand and you refuse to talk. And I told you, do not enter my class without renaming your device. So you have violated the class rule.